Hello everyone! This lesson will introduce you to the most famous algorithm in asymmetric cryptography, the RSA cryptosystem. This lesson will look at a step-by-step example computation of RSA key pair generation, encryption, decryption, digital signature generation, and verification. RSA, named after its creator Ron Rivest, Adi Shamir, and Leonard Adleman, was the first practical realization of an asymmetric cryptosystem, published in 1977. It has since remained the most commonly used, in part because of its suitability for both encryption and digital signature generation. Let's see how keys are generated for use with RSA. In this example, you will have 100-bit long keys for simplicity, but in practice they are often 2048 or 4096 bits long. To get a private and public key pair, first you need to choose two distinct large prime numbers, P and Q, and then compute their product n. The result in n is roughly twice as long as the initial factors. The number is referred to as the public modulus. Next, you need to compute the Carmichael totient function for n. It is a difficult computation in general case, like this example fails after 10 seconds, but with the knowledge of factors p and q, it is simple. Next, choose a public exponent, a number e between 1 and the Carmichael lambda that is coprime to lambda, that is, has no common divisors with lambda except 1. Conventionally, a prime is chosen here because it has no divisors other than 1 in itself, so you only need to check if lambda is divisible by the chosen exponent e. In practice, a particular default value is recommended by cryptographers, and it's often used in public exponent. It's 65537. This default is useful for optimized software and hardware implementations of RSA because it reduces greatly the bit complexity of every future encryption and decryption by having only two non-zero digits in its binary representation. Next, compute the private exponent, which is the inverse of the public exponent modulo our Carmichael lambda. Well, that's it. Your key pair would look as following. The public exponent e and public modulus n are shared with others, while the private exponent d has to remain secret. The key generation for RSA is a complicated multi-step process that only has to be done once. After the key pair is computed, every future encryption and decryption is simply modular exponentiation. RSA encrypt function here takes the plaintext and raises it to the power of the public exponent, while the RSA decrypt function raises the ciphertext to the power of the private exponent. Since the RSA algorithm uses modular arithmetic to ensure one-to-one unique correspondence between the plaintext and the ciphertext, the plaintext has to be smaller than the modulus. Otherwise, the encryption may wrap around. For instance, these three plaintexts would produce the same ciphertext in an RSA cryptosystem with a public exponent 3 and modulus 357. This happens because they are equivalent, so it's congruent modulus 357. For this reason, in practice, RSA is restricted to messages smaller than the public modulus of the key pair. So we'll add to our RSA encryption function a check on the plaintext length and make it throw an error message if that is too long. The RSA decrypt function will stay the same. Since so far we have only implemented RSA for integers, to be able to encrypt text messages, we will need to define helper functions to perform conversion between strings and integers. So we'll use message to int and int to message functions. Now let's see how all of that works together. First, encode the plaintext into an integer. Next, encrypt it with the public key, and decrypt back with the private key. Decode the integer back to a text message, and see it's the same message. As expected, if we try it for a longer message, the encryption will fail and issue an error just as we defined before. Generation of digital signatures with RSA is very similar to encryption, but with the private key applied first to sign and the public key to verify. Here, the RSA sign function takes the plain text and raises it to the power of private exponent, and the RSA verify function checks if the signature is valid for this message and particular public key. In digital signature generation, there is no need for one-to-one inversion, so there is no restriction on the message length. Instead, hash functions are used to create a short thumbprint of the message within the limits of the modulus. Let's try digitally signing a message with our simple RSA cryptosystem. First, encode the plaintext message into an integer. Then, create a digital signature for it with your private key. Next, verify the signature for the message with the public key, and it gives true. As expected, for a different message, the verification gives false. In the next lesson, you will learn how each of the steps of the RSA computation contribute to its security.